All right, this is section 1.2, all about functions. So we're going to talk about some key features of functions, and we will determine if a relation is a function and find its intercepts, domain, and range today. So the definition of a relation, a set of ordered pairs x, comma, y, is always called a relation in x and y. It shows a relationship. So we have a table that shows the score, y, that a student earned on an algebra test based on the number of hours, x, spent studying 1 week prior to the test. So we're going to write the set of ordered pairs that defines the relation. So it's a set of x and y. So 8, 92 is our first point. 3, 58. 1198. 572. And 886. The next question asks us to write the domain. Now, a quick reminder that domain is all possible x values. And generally, we're going to want to put our domain in the order smallest to largest. Since this is just these certain sets of numbers, we're going to put them in these braces. So our smallest number in the domain is 3. And then we have a 5. And then an 8 and 11. And there's our domain, 3, 5, 8, and 11. Now the range is very similar to that. The range is all possible output values or y values. And again, we'll want to go smallest to largest in this case. So the smallest value in our range is 58. And then we have 72, 86, 92, and 98. Notice that our domain is smaller than our range. That's okay because one of the numbers in the domain was repeated. All right, so let's define a function. Let's focus that just a little bit. Sorry about that. There we go. Given a relation in x and y, we say that y is a function of x if for each value of x in the domain, there's exactly one value of y in the range. Your x values have to be mapped to a unique y value. Each x is paired with a unique y value. Means that no y's are repeated. So let's determine if this relation defines y as a function of x. Well, I look at my x values. All of those x values are different, which means no x value is mapped to two different y values. So yes, this is a function. Our second one here is an image. The first set is our x values, the second set is our y values. This one is not a function because the input of 4 is mapped to two different outputs, specifically 3 and 4. You want to get in the habit of using a numerical example in all of these justifications because that's what AP Precalculus will require. Now let's talk about the vertical line test. The graph defines y as a function of x if no vertical line intersects the graph in more than one point. So basically, if I can drag a vertical line across the graph and it only touches the graph one time anywhere, then it is a function. So let's look at these. For my first one, if I take a vertical line, it crosses twice. And all I need is one example of where it crosses twice. It is not a function. All right, let's try the next one. Everywhere on my graph, my vertical line only crosses once. So this one, yes, it is a function. And my third one, checking all the way across, What about right here? Well, my function's not actually defined at that open circle. It is defined at this closed circle, so my vertical line only crosses once anywhere. So yes, that is a function. Now we're going to look at some equations. And hopefully some of these shapes seem similar to you, or familiar to you. X squared plus y squared equals 25. That is actually a circle centered at the origin with a radius of 5. So the question is, does that pass the vertical line test? Not at all. That is not a function. The next one is an absolute value. An absolute value graph, well, the absolute value of x, looks something like a v. Well, that passes the vertical line test everywhere, so that one is indeed a function. So now we're going to use function notation. We're going to evaluate the function h of x equals negative 4x squared plus 3x for our given values of x. So to find h of negative 3, I'm just going to plug negative 3 into h of x for all of the x's. So I have negative 4 times negative 3 squared plus 3 times negative 3. Order of operations, right? We start with our square, so that becomes a 9. Then we do our multiplication, so I get negative 36 plus negative 9, which makes negative 45. H of negative 3 is negative 45. Now let's try h of t. Well, I plug in t for all my x's. Negative 4 times t squared plus 3 times t. All I did was switch the variable, and that's all I can do. There's my answer. And for a plus h, I'm going to plug in negative 4 times a plus h squared plus 3 times a plus h. Now we have to simplify this, square it out, distribute, all that fun stuff. So let's square out a plus h. And one of the most common things I see is that people try to tell me this is a squared plus h squared. No, 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 no. It is never a squared plus h squared. You do not distribute a square into adding and subtracting. It's better to write it out twice and then remember that we have to FOIL. First, a times a is a squared. Outside, a times h is ah. Inside, h times a is also ah. And last, h times h is h squared, which combines to make a squared plus 2ah plus h squared. So that's a little side work I did for a plus h squared, because that's the first thing we should have done. Now we're going to distribute. We're going to distribute the negative 4 and then distribute the 3 into that other set of parentheses. So I have negative 4a squared minus 8ah minus 4h squared plus 3a plus 3h. Now I would combine any like terms I have, but I don't have any, so there's my final answer. It's just got a's and h's inside of it now. All right, using function notation, we're going to talk about finding intercepts. So if I'm given a function defined by y equals f of x, the x-intercepts are the real solutions to f of x equals 0. So set the equation equal to 0 and solve for x. The y-intercept is given by f of 0, so plug in 0 for x. Remember to write your intercepts as points. So when you write them as points, the x-intercepts are going to be a number, comma, 0, and the y-intercept will be 0, comma, a number. Make sure you always write them as coordinates, because otherwise they're not intercepts, they're just numbers. So let's find our x and y intercepts for each of these functions. Let's start with the x-intercepts of x squared minus 5. So I set the equation equal to 0, and then solve for x. Well, to solve for x, I add 5 to both sides. I get 5 equals x squared. To undo my square, I take a square root. And when I square root 5, I get positive or negative square root of 5. Which means my two intercepts there are positive square root of 5, 0, and negative square root of 5, 0. When we solved, yes, we can write it the lazy way with a plus or minus, but when we write the intercepts out, we have to actually separate it, write the two different intercepts. Now to get the y-intercept, we're just going to find f of 0, which in this case is 0 squared minus 5, which is negative 5. So that coordinate is 0, comma, negative 5. All right, next up we have f of x equals the absolute value of x minus 5. To find our x-intercepts, we set f of x equal to 0. Then we add the 5 to both sides. If 5 is equal to the absolute value of x, well then x could have been 5. Or remember that x could have been negative 5 because the absolute value of negative 5 also comes out positive. So two x-intercepts, 5, 0, and negative 5, 0. Then we're going to find our y-intercept by finding f of 0. The absolute value of 0 minus 5 is negative 5. So our y-intercept again is 0, negative 5. And finally we have negative 2 square root of x plus 6. Let's start with our x-intercepts. Set the equation equal to 0. We'll subtract 6 off both sides. And then we'll divide that negative 2 on out. We get 3 equals the square root of x. To undo a square root, we square both sides. We get x equals 9. So there's only one x-intercept. It is 9, 0. And then we find our y-intercept by finding f of 0, which is negative 2 times the square root of 0 plus 6. Well, the square root of 0 is 0. So we just have negative 2 times 0 plus 6, which means we have 0 plus 6, which means we really just have 6. My y-intercept is 0, comma, 6. All right, now we're going to talk about domain. So to find the domain of a function, generally we're going to find the implied domain. Implied domain means that there are restrictions that it doesn't come right out and tell you, but we have to be smart enough to figure out, oh, these restrictions exist. There are two cases to look for. First, we have to exclude values of x that make the denominator of a fraction 0. You can't divide by 0, the world will explode. Then we also have to exclude values of x that make the radicand negative within an even indexed root. So what that means is we can't have a negative inside of a square root. So for this first one, we're going to set the denominator equal to 0. And then the domain is everything but that. For the next one, to make the radicand negative within an even indexed root, usually we'll be talking about square roots, but it could be a 4th root or 6th root or 8th root. We're going to put inside the root has to be bigger than 0. If you solve that, you have found the domain. Remember, that's for a square root, a 4th root, a 6th root, on and on and on. And then we always write our domain as interval notation. So let's find our domains. First one, we have a fraction, which means the bottom can't be 0. So what makes 3x plus 1 equal to 0? I like to write doesn't equal because that's what it can't equal. Well, I subtract my 1. 3x can't equal negative 1. I divide by 3. X can't equal negative 1/3. So to write that x can't equal negative 1/3 in interval notation, we start at the smallest possible number that it can be, which is negative infinity. Our issue is at negative 1/3, so we put a parenthesis because it can't be negative 1/3, but it picks up right on the other side of negative 1/3 all the way up to infinity. That is how we write our interval notation to exclude just one value. For g of x here, we have x squared over 5. Well, there's no roots, so I don't have to worry about that. But what makes the denominator 0? Well, nothing turns a 5 into 0, so our domain is all real numbers, which is just negative to positive infinity. For k of x, we have a square root, which means the inside of the root needs to be greater than or equal to 0. Uh-oh, and I just realized I wrote one wrong thing on this last slide. Inside the root has to be greater than or equal to 0. It can equal 0. I apologize for that. So x plus 3 has to be greater than or equal to 0. Subtract 3 off each side. X has to be greater than or equal to negative 3. So to write that as an interval, I start at negative 3 with a bracket up to infinity. For h of x, we have a denominator, so we have to figure out what makes that denominator 0. So 2x squared plus 3x cannot equal 0. This is one where we have to factor. We're going to factor out the greatest common factor of these two terms, which is x. That leaves us with 2x plus 3. Then we set both pieces equal to 0. So x can't be 0. There we go. And 2x plus 3 can't be 0. Well, we have to solve the 2x plus 3 by subtracting 3 off each side. So 2x can't equal negative 3. And divide by 2. So x can't equal negative 3 over 2. When we write our interval notation with two places that x cannot be, we're still going to start at negative infinity. And we've run into our first issue, the smaller of the two, which is negative 3/2. Or, then we pick up at negative 3/2 on the other side. But then we run into another issue at 0, so we go negative 3/2 to 0, or 0 to infinity. So it's the same thing, we just have more places to split. And finally, for r of x, if I look at r of x, I notice I have a denominator and I have a root. That root happens to be in the denominator, so that means inside the root has to be greater than 0, but it can't be equal to 0 since it's in the denominator. So now I just solve this. 2x has to be greater than negative 7, divide by 2, so x has to be greater than negative 7 over 2. So this one gets a parenthesis, negative 7 over 2 to infinity. And now some graphical behavior of our functions. A function is increasing if, as the input values increase, the output values always increase. So if a is less than b, so if I'm talking about left to right, then f of a is less than f of b. So left to right, it goes up. Decreasing as the input values increase, the output values always decrease. So if a is on the left of b, then f of a will be greater than f of b. So going left to right, it's going down. Then we have these new words about concavity. A graph is concave up if the rate of change is increasing. So if you think about this, we're going down, 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 but it's kind of flattening out, and then up, 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 and it's getting steeper. The rate of change is getting bigger the whole time. I also think of concave up as like this would hold water like a cup. Concave down, the rate of change is decreasing. It's kind of like your flipped over cup. We're going to answer some questions about a graph right here. First thing we're going to find is f of negative 2. So my x value is negative 2, my y value is 1, so my answer is 1. F of 4, my x value is 4. What's my y value? Well, that's an open circle. That's undefined. All x for which f of x equals 3. That means when my y value is 3, what is my x? Well, my x was negative 4, so there's my answer. All x for which f of x equals 1. Well, this one, I have anything between these 2 points. Anything between negative 3 and negative 1. So we'll just say x equals the interval from negative 3 to negative 1, including both endpoints because our y value is 1 at both of those endpoints. The x-intercepts, that's where it crosses the x-axis. It crosses at 0. That point is 0, 0, remember? The y-intercept, where we cross the y-axis, is also 0, 0. Domain. To find domain from a graph, we want to look at the possible x values from left to right. This arrow implies that it goes on forever to the left and up. So it starts forever to the left, which is negative infinity. And the furthest to the right that we can go is where this open circle is, which is 4. Since it's an open circle, we have to have a parenthesis because it does not include it. And then range. Range is the possible y values from lowest to highest. So the lowest possible y value is -4, but we don't quite hit that. So we do -4 with a parenthesis. And the highest possible y value, we had an arrow going up forever, so that is infinity. And finally, we're going to talk about some behaviors of our graph. We're going to determine where this graph is increasing, decreasing, and the concavity. So our graph is increasing when from left to right it is going up. Well, it is increasing right here. We always list the intervals of increasing as x values. So it starts increasing at -2 and it stops increasing at 0. We'll go -2 to 0. This is one of those blurry gray areas of precalculus where you can use parentheses or brackets to enclose these intervals and it won't make a difference. Either way is accepted. Now I look at my graph to see if there's anywhere else that is increasing. Well, it is increasing right here on this part. So that's an x value of 4 until my x value of 7. So I put a u, 4 to 7. And there we have our increasing intervals. Decreasing, very similar, just where it's going down. Well, it is going down from left to right on that piece right there, which starts at -4 and ends at -2. So -4 to -2. And then it starts going down again here. Even though it does something funky, it's still going down. So it's going down from x being 0 until x is 4. So our second interval is 0 to 4. Now we look at concavity. Concave up, remember it's kind of like a cup where it could hold water. Well, right through this piece, that is concave up. So we'll say the x values again, 2 to 7 is where it's concave up. Concave down is like the flipped over version of that. It would dump the water out right there where it's upside down from -2 to +2. Notice that the straight line part isn't concave up or concave down. It doesn't have a concavity. Now we have to look for where h is both increasing and concave up. So basically where my pink, my dark pink here, and my green are overlapping. Well, 4 until 7, it was both concave up and increasing. 4 to 7. H is both decreasing and concave up. Oh no, I answered the wrong question. I wanted increasing and concave down. So dark pink and light pink. That's my fault. That's this piece of the graph right here. So -2 to 0. Now, decreasing and concave up. Decreasing is my dark blue, concave up is my green. Where did those two overlap? Well, decreasing and concave up right here from 2 to 4. And the very last thing we're going to do here, we are going to sketch a graph using some given information. The graph is increasing on the intervals, you can't see those. So what those intervals actually are, we are increasing on the interval, first one is -4 to 1, and the second one is 5 to 7, and is decreasing on the interval 1 to 5. Additionally, the graph is concave up on the interval 3 to 6, and concave down on the intervals -4 to 3 and 6 to 7. There we go. Now that we have all the information, we can actually sketch our graph. So I'm going to draw myself a little key down here at the bottom, starting at -4 over to 7, just to kind of help myself visualize what's going to be going on. There we go. So from -4 to 1, I am increasing. So -4 to +1, I am increasing. Left to right is going up. And from 5 to 7, so 5 to 7, I am also going up. On 1 to 5 here then, I'm going down. So my graph has to do something like that. It has to go up, down, up. All right? For concavity, 3 to 6, so that's 3 to 6, we are concave up, like that. And then negative 4 to 3, we are concave down. And 6 to 7, we are also concave down. So now we have to try to put all that together. So all right, I'm concave down, so my graph is kind of going downward, but I'm also increasing. So my graph starts off going like this. But then right here at 1, it stops increasing. So I'm going to go up until I hit 1. And I stay concave up for a little bit, but I'm going to start going down. And at 3, I have to switch to concave up, but I have to keep going down. So I have to kind of like that. And at 5, I start going up again. And at 6, I switch to being concave down again, but still going up. Ignore that piece. That's a sketch of what my graph could look like. Sketching the concavity is the trickiest part.